Moving on now to Calculus Lesson 7. We now know pretty well how to differentiate everything. So we've learned all the different techniques of differentiation. Now we're going to learn how they apply. So what do they mean? How do we use them? When do we use them? Why do we use them? This is where calculus really starts to get interesting. For applications of differentiation, just to warm us in, I want us to just go about finding the derivative of y equals x squared minus 4x minus 5, like we've done. So you should be able to see that that's just vanilla differentiation, and that becomes 2x minus 4. All good. That there is what we're going to call the family gradient. And what that means is it's not specific to any point, it applies to the whole curve. It's the derivative of the whole curve. It's the family gradient. Okay? With another question like this, if I add on find the gradient of the tangent, remember derivative and gradient of the tangent are the exact same thing. If someone says what is the derivative, they're asking what is the gradient of the tangent. So find the gradient of the tangent to y equals x squared minus 4x minus 5, same curve as above, at the point x equals 1. In order to do that, we just write out our function. We differentiate it to get our family gradient, so that applies to everywhere in the curve. And then, if we want to know specifically at x equals 1, we sub x equals 1 into that family gradient, and we'll get our specific gradient. Now these are just names that I call them, but it just helps you to understand it a little bit. So it's the specific gradient at that particular point in the curve, x equals 1. So let's do that. We sub x equals 1, we just replace 1 into all our x's. We get 2 minus 4, which is just minus 2. So in the next step, I actually write, therefore, m of t, and the reason I say m of t is it's just gradient of the tangent, but it's nice shorthand to use that. And why I actually go about writing that, this is again my own little technique, but I like to show the difference between my family gradient and my specific gradient. So once I've subbed it in and I get my specific gradient, I call that m of t as opposed to just y dash. Y dash I like to think of as my family gradient, m of t, or the gradient of the tangent, is my specific gradient. So we found that our gradient of the tangent at x equals 1 is negative 2. M of t is equal to negative 2. That's how we do it algebraically. Just to give you an idea graphically of what we're talking about, what I've done there is I've just sketched that curve, y equals x squared minus 4x minus 5, just a parabola. What they're basically asking is at the point x equals 1, at that point over there, what is the gradient of the tangent to the curve? So there is the tangent to the curve at x equals 1, and the gradient of that is going to be minus 2, exactly like we just worked out, which makes sense because it's a negative gradient, it's a little bit steeper. It all makes perfect sense if you actually look at graphically and algebraically. Now, it's not essential that you go about doing that graphically. I've just done it for you here to make it a little easier to understand. Let's take this a little further. The question asks us to find the gradient of the tangent of f of x equals x into 1 minus 2x squared at x equals negative 2. So they're asking for the gradient of the tangent, in other words the derivative, but specifically when x equals negative 2. So we know we've got to differentiate it. We've got to differentiate that function there, and in order to do that we should go about it in the way that we just learnt in our art of differentiation lesson, and ask ourselves the question, will it easily combine? Well, this one here, it actually will. That squared is a nice little bonus because with a squared we can quite easily expand that through. If it was a cubed or to a 4 or a higher indice, that x wouldn't be able to times through. We wouldn't be able to expand it out, and it would therefore be non-expandable, and it would be a product rule. And ultimately this could be done as a product rule, but it's a lot easier if you can see how to expand that. And what we do is just expand that bracket. So we do the first squared plus twice the product of the two plus the last squared. And in the next step, we tidy it up. So I try not to skip steps where I can. So it's still x into 1 minus 4x plus 4x squared. Then I can expand the x through. X minus 4x squared plus 4x cubed. So I still haven't differentiated it yet. It's still f of x. But I've set this up into a great position in order to do so, because now all it is just our vanilla differentiation. So let's differentiate that. We get 1 minus 8x plus 12x squared. That there is our family gradient. That applies to anywhere on the curve, not specific to a point. But they have asked us for a specific point. They said at x equals negative 2. So if we want to find out, let's sub at x equals negative 2. We'll sub it into there. So we'll do f dash of negative 2. So wherever there was an x, we replace it with a negative 2. As you can see, not skipping steps, sub in the negative 2 in whole. In the next step, we'll expand it. So it becomes 1 plus 16 plus 12 into the minus 2 squared is 4. 12 times 4 is 48. And then we add them all up and we'll get 65. So you can see I've written my m of t there because that is my specific gradient. So what I like to do, as I mentioned before, when I get my specific gradient, I show a difference between my family gradient, which I called f dash x or y dash, and my specific gradient, which I like to call m of t or gradient of the tangent, or you can call it whatever you want really. It's just nice to have that differential so you know that this is a gradient at a specific point. So ultimately, just to summarize that, the gradient of the tangent of that curve at the point x equals negative 2 is 65. So it's a very, very steep gradient at that point. Okay, next one. Find the equation of the tangent to y equals 6 minus x squared at minus 1, 5. So a couple key differences here between this and the last question. First one being, it says find the equation, not find the gradient of the tangent, but find the equation of the tangent to y equals 6 minus x squared. So we want to go beyond just finding the gradient, but actually then go ahead and find the entire equation of the tangent. The other difference is, instead of just saying at x equals negative 1, here it's given you the specific coordinate at negative 1, 5. So it's given you the x and y coordinate, which is helpful. So you don't have to go chasing that y coordinate just yet. Okay. Our y equals 6 minus x squared. We know we first got to find the gradient of the tangent before we can find the equation. To find the gradient of the tangent, we know we've got to differentiate it. It's just nice vanilla differentiation. So it's minus 2x. That there is our family gradient, as we call it. If we want to get our specific gradient, we've got to sub in our specific point. So we sub in at x equals negative 1, because that's the x value. We put that into our y dash. Wherever we had x, we replace it with negative 1. And so our m of t, or our specific gradient, or our gradient of the tangent at that specific point is 2. So that is our gradient of the tangent. That's what we've done so far. Now, as I said, the extension in this question, they say find the equation of the tangent. So we know from coordinate geometry a couple years ago that when we want to find the equation of a line, we've got to use our equation of a line formula. And the formula y minus y1 equals mx minus x1 is the best one to use. It's known as our point gradient formula. Why is it known as that? Well, when we find it, we need to find a point and a gradient in order to find the equation of the line. Hence the point gradient formula. Pretty innovative naming technique there. Okay. We know we've got to use that formula. So we write that formula out every single time they ask for an equation of any line. We then, because it's a formula, we do our chopping board. We know our x1 is -1 and our y1 is 5. Easy because they're given it to us here. Our m, which is what we just worked out, and that's another reason why I call it m of t and I give it its own name. The reason I call it m of t is because it is ultimately an m. It is ultimately our gradient. So the m is 2, and now we can sub it all in. Perfect. We can expand through the negative and the negative, make the positive, and then expand the 2 through. Y minus 5 equals 2x plus 2. Put the 5 on the other side, y equals 2x plus 7. Okay, that there is the equation of the tangent to that curve. They may ask us to convert it to general form, in which case it would be 2x minus y plus 7 equals 0. Now, if you've forgotten our different forms from year 10 coordinate geometry, here's a quick review. Our two forms of a line are general form, which is ax plus by plus c equals 0. And that is the key there. General form just means everything equals 0. So just put it all on one side, equals 0, you got your general form. And that is that form there. The gradient intercept form is our old school formula, our y equals mx plus b. With our gradient intercept form, it's y equals mx plus b. That's our old school formula. And it's called gradient intercept because pretty much like our point gradient from before, it's called that because it's the gradient and the intercept. Remember, b is our y-intercept. And that's where they get the name from, the gradient intercept form, because those are the two things that we need to find. That is gradient intercept form there, y equals. So to get gradient intercept form, you have y equals mx plus b. With general form, it's everything equals 0. Next one, and this applies to all of them, the try it yourself first icon at the top there. If ever you want to attempt it yourself before you see it done, absolutely go for it. I encourage that very, very highly. Rather have a go and fail and then see how it's done than just try follow the whole way and not actually put it into practice. So this one, I definitely want you to pause me and try it yourself first. But if you want to try that at any stage, I'm encouraging of that. So let's see how you did. Find the equation of the tangent to y equals 2 minus 4x plus x cubed at x equals 2. So we know this is a very similar one to the one we just did. First things first, we've got our y equals 2 minus 4x plus x cubed. We need to differentiate that. We need to find the derivative, which is minus 4 plus 3x squared. That there is our family gradient. It applies to the whole curve, not yet specific to a point. In order to find it specific to a point, to our specific gradient, we sub in that specific point that we want. In this case, it's x equals 2. We sub that in to our y dash, and we get minus 4 plus 3 into 2 squared. We just replaced any x's with 2's. Next step, minus 4 plus 3 into 4. See, I'm not doing anything too fast, one step at a time. Minus 4 plus 12, which leaves us with 8. So in other words, our m of t, or our gradient of our tangent, or our specific gradient, is 8. Now, they want us to find the equation of the tangent. So as soon as we hear the word equation, we think of our equation formula. This, just to remind you, is our point gradient formula, because there's a point and a gradient. Y minus y1 equals m, x minus x1. Write it out every time. Because it's a formula, we do our chopping board. x1 is 2. They've given that to us. The difference between this and the last one is they haven't given us our y value. But in order to do that, we just sub it in to our y to get our y value. We sub our x back in, so wherever there was an x in the y, we replace it with a 2. So it becomes 2 minus 4 into 2 plus 2 cubed. Next step, 2 minus 8 plus 8. The 8's cancel, so y1 is equal to 2. Our m, which we just worked out, is equal to 8. All our ingredients are there. Sub them in. Y minus 2 equals 8 into x minus 2. We can then just expand that through. Y minus 2 equals 8x minus 16. And then y equals 8x minus 14. So that one I've just decided, because it's nice and neat, I've just decided to leave it in gradient intercept form. Y equals mx plus b form. Perfect. Hopefully that one went well. Now, let's amp it up a bit. Final question of the lesson. Find the equation of the normal to y equals root 2x minus 2 at x equals 3. Now that is a little bit of an intimidator because there's a couple new things there. In fact, I've thrown in as many curveballs into that as I can at this stage. So if you can answer this, or you could follow the working of this, you're pretty much set. So let's give it a go. Again, if you're feeling on top of the work, it's a really good time to try this yourself and see how you go. Worst case, you fail at it, and then you can see how it's done. But it's always, always, always good to try it before you see it. So, firstly, we're going to write that out and obviously differentiate it. We need to try find the gradient of the tangent, or the derivative. In order to differentiate that, we know we can't work with roots. We get it into index form. That now is a chain rule. So we bring down the power, minus 1 from the power, and times by the derivative of the bracket. We then tidy it up. So the 2 times is by the half, and we just left with 2x minus 2 to the negative half. So that's the derivative. Now, it's actually going to be easier to work with in terms of subbing stuff in when it's back in its original form with roots, and so no negative and fractional indices. So look, you can just sub it into there, but I'm just going to convert it back into its original form. So first things first, I get rid of the negative indice, so I make it 1 over. In other words, I take it all down and I get rid of the negative. Then I want to get rid of the fractional indice. And the way you do that, a half is just a root. Okay. There is my y dash, my derivative, my family gradient, if you will. Now when I want to know my specific gradient of the tangent, I sub in my specific point, which is x equals 3. Sub that into there, so whether there was an x, I replace it with a 3. And I'll end up expanding, so you get 1 over root 6 minus 2, 1 over root 4, which is 1 over 2. And that is my gradient of my tangent. So we know that my m of t is a half. And now we want to know our m of n, because we're actually looking not for the tangent but for the normal, as I said. Hopefully you remember the relationship between tangents and normals. Just in case you don't, I'm going to do a quick recap. Here's a curve, f of x. There is a tangent to the curve. So that's the gradient of the tangent. There's a normal to the curve. And you should know that normals and tangents are perpendicular to one another. They bisect at 90 degrees. And what do we know about perpendicular lines? It's that they have negative reciprocal gradients. What does that mean? Well, for example, with the gradient of the normal there, it's equal to negative 1 over the gradient of the tangent. So if the gradient of the normal is, say, 3, the gradient of the tangent is negative 1/3. Negative and flipped over. If the gradient of the normal is 7 on 2, the gradient of the tangent is negative 2 on 7. If the gradient of the tangent is negative 1/4, then the gradient of the normal is 4. So that hopefully makes sense. You flip it over and give it a negative. And so if we've got our gradient of our tangent is a half, then our gradient of a normal is going to be, you should be saying negative 2. Okay, now we're ready. We've got our gradient of our normal, but they want us to find the equation of the normal. So we write out our equation formula, we do our chopping board, we know our x1 is 3. Our y1, we need to sub back in our x into our y equation. So we sub in 3 into our y. We get root of 2 into 3 minus 2, which is root of 6 minus 2, which is root of 4, which is 2. So our y1 is 2. And then we know now that our m of n, or our m, is negative 2. Chop import done, sub them all in. And now at this stage, you can actually go and do general form or gradient intercept form. It doesn't really matter, both are correct. For me personally, unless I'm asked for a specific one, I normally just choose the neater one. So default, that's the gradient intercept form, y equals is neater. But if there are fractions, such as here, I normally actually convert it into general form, because you don't want y equals a third x of plus 3/5. It's just a bit uglier. So in this case, where we've got fractions, I'll actually go into general form. And we'll do that by getting rid of that half. So in other words, we times both sides by 2. Okay? So we do that there. We times through both sides by 2. That becomes 2y minus 4. And the half cancels. So it equals x minus 3. Then we put everything onto the one side. So that leaves us with x minus 2y plus 1 equals 0. As I said, it doesn't really matter if that's in general form or gradient intercept form, both are correct. And that's perfect. Perfect, perfect, and really not an easy question, as hard as it'll get at this stage. So if you're following that, you're killing it.